And the sheer magnitude of energy generated by the Raptor 3 pre-burners is, in isolation, a liability. Without a mechanism to throttle, redirect, and balance that energy, the engine is less a machine and more a directional bomb. To transform this chaotic release of chemical potential into a stable, steerable column of thrust, the engine requires a nervous system of unparalleled fidelity. This is the domain of fluidic orchestration, a realm where valves act as logic gates and sensors serve as the sensory cortex for a real-time, high-frequency control loop. And the fluidic conductor, orchestration at kilohertz frequencies. If the pre-burners are the engine's percussion, the control system is the master conductor. In a symphony, a conductor ensures that 100 musicians strike their notes within milliseconds of one another to create harmony rather than noise. In the Raptor 3, the musicians are thousands of individual fluid particles, and the notes are the precise pressure set points required to maintain combustion stability. And the challenge of orchestration in the Raptor 3 is exacerbated by the fluid dynamics of the full-flow staged combustion cycle. Because every drop of propellant is gasified before it reaches the main chamber, the system lacks the damping effect of liquid inertia found in simpler engines. Gaseous flow is twitchy. It responds to pressure changes at the speed of sound. Consequently, the control system must operate at a temporal resolution that exceeds human perception. And the engine's flight computer, the Engine Control Unit, or ECU, is constantly solving a multivariable calculus problem. It must modulate the flow of cryogenic liquids into the pre-burners, while simultaneously managing the output of the turbines and the pressure of the main combustion chamber. If the oxygen-rich side begins to lag behind the methane-rich side by even a few milliseconds, the resulting mixture ratio shift in the main chamber could lead to a lean-out or a rich extinguishment, either of which would cause the engine to flame out or, worse, melt the injector plate. And valves as logic gates, the architecture of control. In traditional mechanical engineering, a valve is a simple component, a gate, that opens or closes to allow fluid through. In the context of the Raptor 3 hardware logic, however, these valves function more like transistors in a microprocessor. They are the physical embodiments of if-then statements. And if the turbine inlet temperature exceeds 750 degrees Celsius, then increase the methane bypass flow to cool the gas. If the chamber pressure drops below 300 bar during the throttle-up command, then tighten the main oxygen valve to sharpen the mixture ratio. And these are not binary on-off switches. They are high-bandwidth, proportional integral derivative-controlled actuators. In earlier iterations of the Raptor, these valves were often bulky, pneumatically or hydraulically actuated components that required complex support lines. In the Raptor 3, SpaceX has moved toward high-torque, fast-acting electric actuators integrated directly into the valve bodies. This shift eliminates the latency inherent in fluid-driven systems. An electric signal travels at the speed of light. A pneumatic signal travels at the speed of sound through a tube. By switching to electric control, SpaceX has reduced the systemic ping, allowing the engine to respond to instabilities before they have the chance to propagate through the plumbing. And from spaghetti to silicon, the integration revolution. To understand the leap between Raptor 1 and Raptor 3, one must visualize the evolution of the computer. The early ENIAC computers were a mess of external vacuum tubes and tangled patch cables, what engineers colloquially call spaghetti code in physical form. Raptor 1 was similar. It was a marvel of engineering, but it was covered in a dense web of secondary plumbing, external sensors, and exposed wiring harnesses. Every one of those external lines was a failure mode, a potential leak point, a vibration-sensitive joint, or a thermal vulnerability. And the Raptor 3 represents the single-chip era of rocketry. Through advanced additive manufacturing and a philosophy of radical consolidation, SpaceX has moved the logic of the plumbing into the hardware of the engine body itself. And in Raptor 3, the sensors are not bolted onto the outside of the pipes. They are often embedded within the walls of the components they monitor. The plumbing is largely internal, 3D printed directly into the structural castings of the turbopumps and the main chamber. This integration serves three critical purposes. In mass reduction, by eliminating hundreds of bolts, flanges, and brackets, the engine's dry mass is significantly lowered. Thermal protection. External wires and tubes are vulnerable to the convective inferno of the engine bay during flight. Internalizing these paths uses the engine's own structure as a heat shield. Reliability. In software, a thread-safe program is one that can handle multiple simultaneous executions without crashing. By removing external lines, SpaceX has made the engine physically thread-safe. There are fewer joints to vibrate loose under the 100 G loads of liftoff and fewer seals to fail under the extreme thermal cycling of re-entry. And the real-time control loop, preventing the kernel panic. In the world of operating systems, a kernel panic occurs when the core software encounters an internal error from which it cannot recover, leading to an immediate system halt. In a Raptor engine, a kernel panic is a catastrophic structural failure, an unscheduled disassembly. And the Raptor 3 ECU prevents this through a high-frequency feedback loop. The engine is littered with transducers, pressure sensors, thermocouples, and accelerometers that feed data into the ECU at rates often exceeding 10,000 samples per second. This data is compared against a digital twin, a mathematical model of what a perfect engine should be doing at that exact microsecond. And if the sensors detect a pressure spike in the oxygen-rich preburner that doesn't match the model, the ECU doesn't wait for a human to intervene. It initiates a subroutine to mitigate the spike. It might slightly crack a bypass valve or adjust the spark timing. This happens in the background, much like a modern car's traction control system manages wheel slip on ice. The pilot, or the Starship's primary flight computer, simply asks for a certain level of thrust. The Raptor's internal logic handles the low-level hardware abstractions required to deliver that thrust safely. And this level of autonomy is what allows Starship to perform its signature belly flop and landing burn. During the flip maneuver, the engines must ignite, throttle, and gimbal with extreme precision while being tossed around by massive centrifugal forces. The fuel in the tanks is sloshing, the pressures are fluctuating, and the orientation is changing rapidly. A dumb engine would choke. The Raptor 3, with its high-speed control loop, shouts through the noise, maintaining its internal equilibrium despite the external chaos. And the aesthetics of efficiency. The clean engine, when you look at a photo of the Raptor 3, the first thing you notice is how clean it looks compared to its predecessors. It lacks the steampunk aesthetic of the Space Shuttle main engine, or even the early Raptor 1. This is not for the sake of beauty. It is the ultimate expression of manufacturing simplification. And every external component on a rocket engine is a liability during the rapid reflight cycle. If an engine has 1,000 external parts, you have to inspect 1,000 parts after every flight. By integrating the sensors and valves into the hardware logic of the engine body, SpaceX has reduced the inspection surface area by orders of magnitude. And this integration also reduces physical latency. In a system where a valve is separated from its sensor by 3 feet of tubing, there is a delay in the feedback loop. The pressure wave must travel through the tube to reach the sensor, and the command must travel back. By placing the sensor and the valve in the same integrated housing, essentially on chip, the Raptor 3 achieves a level of low latency control that allows it to push closer to the theoretical limits of the physics. It can run at higher pressures because it can see a failure coming and react to it faster than any previous engine in history. And the digital logic of propulsion. Ultimately, the Raptor 3 treats the movement of mass as the movement of information. The propellant is the data, the valves are the logic gates, and the thrust is the output. This paradigm shift from viewing an engine as a piece of heavy machinery to viewing it as a high-frequency fluidic processor is what sets SpaceX apart. And the plumbing of the Raptor 3 isn't just a way to get fuel from point A to point B. It is a sophisticated network designed to manage the entropy of the system. By minimizing the distance the data, or fluid, has to travel and maximizing the speed at which the logic, or valves, can process it, SpaceX has created an engine that is not only the most powerful in its class, but also the most intelligent. And this intelligence is what makes the stage combustion cycle viable at such extreme scales. In an open-cycle engine, you can afford to be a bit sloppy because the exhaust from the pumps is just dumped overboard. In the Raptor's closed-loop, full-flow system, every milligram of gas is recycled back into the system. It is a highly coupled environment where a hiccup in one area can resonate through the entire machine. Managing that coupling requires the digital-age precision that the Raptor 3 integrated control system provides. And as we have seen, the Raptor 3 is a masterclass in recursive engineering and integrated logic. It takes the raw, violent energy of the preburners and tames it through a nervous system of sensors and valves that operate at the edge of what is physically possible. But to truly understand why SpaceX went to such extreme lengths to perfect this staged approach, and why they refuse to waste even a single gram of propellant, we must look at the fundamental thermodynamic divide that has defined rocketry for 70 years. In 4.1 Open versus Closed Cycles, Why Most Rockets Waste Fuel.